Hello, this is Dr. Viv, and I will be discussing logarithmic derivatives and first order errors. So, take a look at the expression that I have here. It's a complicated function of x involving products and ratios. If you were trying to do this through the traditional techniques of calculus, such as quotient rule or product rule, it will not be easy. It's still doable, but it won't be easy. There's a much better way to do this, and that is, the first step to that would be to take the logarithm of both sides without quite worrying about whether it's well defined or not, because logarithm is only defined for quantities that are bigger than 0, and some of these quantities can be less than 0. So for now, we'll suspend our disbelief and just take the logarithms. Now, if you take the logarithm of a ratio, it'll just be the difference of logarithms, and the logarithm of a product is just the sum of logarithms. So I'll write that out here. So I'll get logarithm sine x plus ln sinh. Now when I take the logarithm of e to the x squared, I'm going to get x squared in the front times the logarithm of e, which is 1. So that's just going to be x squared. And then now for the denominator terms. In the denominator, I have 1 plus x squared to the power 3/2. So 3/2 power comes in front of the logarithms by the power rule of logarithms. So I'm going to get negative 3/2 times natural log of 1 plus x squared. And then I have this term here, so I get negative natural log of cosine x plus x squared. So all I've done so far is taken natural log and made some simplifications using popular values of natural log, such as natural log of e equals 1, and use the product, the quotient, and the power rule of natural logarithms. So just for your reference, I'll put those rules over here on the right side. The product rule of logarithm is something like this: ln AB equals ln A plus ln B. And the quotient rule would be ln A minus ln B for ln A over B. And the product rule, I'm being pretty unimaginative here. I'm just using A and B everywhere, so that's B times ln A, plus a couple other things, and that is natural log of E equals 1, and the natural log of 1 to any base is 0. So once you have these basic properties of logarithms, you can now go ahead and differentiate. The other thing you know about the derivative of a logarithm is 1 over the function. So if you have just on the side, if you have y equals ln x, then dy by dx is 1 over x. So what I can do is I can write this as dy equals 1 over x times dx. So that's basically what I'm going to be doing here. If I have the natural logarithm, then dy equals 1 over x dx. So if I differentiate this in that fashion, so I'm going to get natural log of y is going to be, if I differentiate both sides, then it's going to be dy by dx. So let me just do that. But I'm differentiating natural log of y, not natural log of x. So that's going to be dy by y instead of 1 over x. I'm going to get 1 over y. And on this side, I'm going to have things like dx cosine x dx by sine x, because after differentiating, I'll go and take the derivative of the inner function by what's called the chain rule. And here I'll get the derivative of sinh. Now if you recall that sinh is e to the x minus e to the minus x divided by 2. So if I took a derivative of that, the e to the x remains the same. E to the minus x produces another minus sign to make this a plus. The derivative of sinh is just cosh. So that gives me cosh x dx divided by sinh x. What about here? I'll get just 2x dx, and then that term, so that's going to be negative 3/2. Now if I go inside and differentiate 1 plus x squared, I'm going to get 2x dx divided by 1 plus x squared minus, well, this one here, it'll go to the denominator just like all these other terms, but the numerator is going to be minus sine x plus 2x divided by cos x plus x squared. So we have finished our problem. It might seem hard to believe that you have finished your problem, but all you now need to do is to transfer dx to the other side and y to the right side. So let me take a moment to do that. So I get dy by dx is equal to y times, now cos over sine is cot, and then cosh over sinh is cot. This is just 2x, and here I can make a simplification, so that's minus 3x divided by 1 plus x squared, and I'll move this over there, so I get minus 2x minus sine x divided by cos x plus x squared. And the problem is basically finished at this point. You can substitute any value for x and evaluate it. This is very useful to have when you don't really seek a particularly compact form for the answer, but you're more interested in finding out the value. For example, you want to find the value of y at derivative at pi, for example, or pi over 2. At pi there's nothing to do because this is 0. So that's another important insight it gives you. If the function is 0 at a certain point, the derivative also has to be 0 unless, and let me not make that statement because this part can be infinity, so we have to be careful. But that's a quick way of finding out if you have a 0 or not, and then you can examine it more carefully by looking at the inside terms. What are the practical applications of the logarithmic derivative? There's actually a very important practical application, and that's called first order uncertainties or first order errors. And this goes like this. It's best to probably do this using an example. So here's an example. Suppose, say, vendor offers you, suppose you're collecting coins, and a certain vendor offers to sell you a coin on eBay. Now you're going to buy this sight unseen, so the least you can have is some measurements. So you ask him to or her to send you measurements of this coin. Okay, it's supposed to be pure gold, and the money involved is quite a lot, so you want to make sure you're not spending money on something that is not gold. So you ask the person to give you the mass, the diameter, and the height of the coin. So let's just make some numbers up. Let's say that the diameter of the coin is about 2 inches, so that's 5 centimeters, and since it's measured using a ruler, the errors are going to be something like a millimeter or 0.1 centimeters. Okay, let's say the height is 0.3 centimeters plus or minus, again, 0.1 centimeters. So you can see that if you're using the same ruler, that's going to be a pretty huge uncertainty. And lastly, the seller throws it on a kitchen scale, and tells you the mass is 100 grams plus or minus 1 gram. I mean, it's a kitchen scale, it can't be super accurate. And 100 grams, off the top feels like a good solid weight for this coin, so you might be tempted. Well, let's be careful. Let's first calculate what the density is using density equals mass over volume. So the traditional formula for density is that density rho equals mass by volume. The mass here is m, and the volume is that of a cylinder because it looks like one. It's the base of the cylinder's area. That's going to be pi r squared times the height. Now r is not given, but diameter is given, so that's going to be pi r over 2 squared, which is d squared over 4 times height. Now what I'm going to do is, this looks like a complicated formula just like that. Now rather than assume that it's all a function of x or something else, I'll just blindly take the logarithmic derivative. So this tells me that natural log rho is equal to natural log m minus, I'll club pi over 4 as a single constant, so minus natural log pi over 4, and then I get negative 2 natural log of d minus the natural log of the height. And then I proceed to logarithmically differentiate this, so therefore d rho by rho is equal to dm by m. Constants don't contribute, so that's 2 times d capital D by d minus d capital H over h. And then what I'll do is I'll say negative values are ruled out because we're considering percentage errors. You can't accidentally have errors fortuitously canceling each other out, so that's not that won't be a good thing. So we're going to take the absolute values of this. So delta rho over rho will then be equal to, now this is not great mathematics, but we're trying to find an estimate. So it's delta m over m plus 2 times delta d over d. So what I'm doing is I'm replacing the differentials with deltas, namely changes. So this is why it's called a first order approximation of the uncertainty. Now if you study uncertainties in super detail, you're going to get a square root of the squares of these things. Now the square root of a square is always smaller than just the sum of the quantities. So this actually gives us a bigger error than you actually will get using the laws of statistical errors. But that's fine. The bigger the error, the better protected you are against bad sellers. So now let's calculate these things. So delta m is just 1 gram. You don't have to worry about the units because they cancel out. 1 over 100 plus 2 times, delta d is 0.1, which I'll just write as 1. Let me write it as 0.1, or you might get confused. Divided by 5.0. The centimeters cancel out. The delta h is going to be 0.1 divided by 0.3, and once again the centimeter cancels out. So here you can see almost immediately the relative contributions of these errors. That's one of the advantages of this method. Now 2 times 0.1 is 0.2, divided by 5 is 0.04, and 1 over 3 is 0.33. So as you expect, this is the worst, and surprisingly the kitchen scale is accurate enough because it's the best uncertainty in this computation. You might think the meter stick is more accurate, but this is the best value. So the first order error method allows you to home in on the best and the worst measurements almost immediately. Now it's a job for your calculator. So I have one here. So let me do this. 0.01 plus 0.04 plus 0.33, and that's 0.38. all we now have to do is calculate the rho itself, which is given by this formula. So the mass over pi by 4th d squared times h. So the mass is 100 grams. Now these are the average values, you don't worry about the uncertainties here, divided by pi over 4. D is 5.0 centimeters squared, and h is 0.3 centimeters. And another spell with my calculator. I'll just make pi 3.14 divided by 25 and then divided by 0.3. So 16.985, so I'll write it as 16.99, which is really approximately 17.0 to one significant figure, and the units are grams per centimeter cubed. Let's find the uncertainty. The uncertainty delta rho is going to be the relative uncertainty, which is delta rho over rho, times the value of rho itself, the bare value of rho. Well, delta rho over rho is 0.38, so that's going to be 0.38 times 17, or 6.46. Pretty hefty uncertainty given the lousy nature of the measurements. So the density of your coin can range anywhere from 17 grams per centimeter cubed plus or minus, I'll make this 6.5 to the same amount of precision as the calculation. So it can be something as light as 11 grams per centimeter cube, or something heavier than gold is. If you recall, gold has got a density of something like 19.6 grams per centimeter cube, but gold does fall in this ballpark. So you can give the seller a benefit of the doubt and maybe ask for more precise measurements to be 100% sure.